Okay, if people want to get seated, we're going to start the next session. The next session is Dynamic Reserve Applications. And I'm Debbie Liu. I'm the Associate Director of ESIG. And we've got a really exciting session for you this morning. So as you know, typically we hold operating reserves on a fairly static basis. Traditionally, we've done this, but with increased wind, solar, with the need for posturing the system to prepare for extreme weather events, and probably with increased electrification, we're going to need to think about reserves in a much more dynamic way. And we're going to need to think about defining reserves based on system conditions at any given time, which means those requirements would be dynamic. A couple of years ago, if you had the special issue of the IEEE magazine that we do every couple of years, the November, December issue from 2019, we did a scan of a bunch of systems, ERCOT, Kauai, SPP, Ireland, Australia, and we talked about their move away from static reserves and towards more dynamic reserve requirements, with some of those utilities using very dynamic reserve requirements based on conditions at any given time. And others a little bit more, more on the spectrum towards the static side. And there's been a huge amount of progress since then. And we're going to be talking about some of those developments today. We've heard about some of that this morning already. There was some discussion. Amber, for example, was talking about what they're doing in CAISO, and Tolu touched on New York. And we're going to have a speaker from the New York ISO talk about that in much more depth. So I'm going to start the session with, we're going to change up the order a little bit. Joanne Ranola from Grid Ops and Planning at EPRI is going to be our first speaker. Joanne, she joined EPRI in September 2021, where she's focused on resource adequacy initiatives. And she brings more than 15 years of experience in electricity market modeling, analysis, financial modeling, and business development across various countries around the world. So with that, Joanne, are you online?
Yes, I'm online.
Great. Okay, so I think
thanks, Debbie.
You should be able to share your screen and take it away, Joanne.
Can you see my screen right now?
See your screen and we can hear you as well.
Perfect. Thanks, Debbie. So once again, good morning to all of you. My name is Joanne Ranola, a technical leader here at EPRI. I'm thrilled to present a survey of dynamic adoption of dynamic reserve practices as part of ESIG's 2022 workshop. So without further ado, I will show you the contents of this presentation. We'll start with some of the key definitions, and then we'll have a discussion about the overview of existing dynamic reserve products, particularly short-term RAM products, long-term RAM products, dynamic reserve, contingency reserve, and then this will be followed by some of the methods to determine dynamic reserve requirements. And then to wrap up, we'll provide you some of the summary and also the key references used for this presentation. For the definitions, so how do we define operating reserve? So as we all know, so operating reserve is the active power capacity that is held above or below expected average energy schedules. This is to respond to changing system conditions under operational timeframes. So what you can see on this slide is just a simple figure that I borrowed from one of my colleagues at EPRI. So you have a single resource here showing the energy scheduled, represented by this blue line. And then this single resource has a minimum generation and capacity. And then as the system change, so this single resource has capability to provide upward reserve, meaning it can provide the generation above its energy schedule. In terms, there's a need for additional generation in the system. Similarly, this single resource can also have a downward reserve capability, wherein it has capability to reduce its generation, and again to respond to the, say, reduction in the net load. And for this resource, say one of the constraints is, say, the RAM constraints related to this generation. And then moving on, so what are the types of operating reserves? So there are a lot of ways to categorize operating reserves. Here at EPRI, so this is again another slide that I borrowed in from one of my colleagues at EPRI. And this is how one way for us to define operating reserves. So we can categorize them as event and non-event. So for non-event, so these types of reserves are supports, say, large or rare events. Examples of this one are contingency reserve and the ramping reserve. So for contingency reserve, so this supports instantaneous events such as, say, the loss of the largest generation in the system. And then for ramping reserve, this is more applicable, say, for future systems wherein you have a huge penetration of renewables. And assuming your huge VRE resources in terms of generation has a sudden, say, drop in the generation or sudden increase. And then this can be prolonged over time, which can be also be a rare event in a situation. And so again, to highlight, this ramping reserve supports longer duration events. And you can see here, so this contingency and ramping reserve can be further categorized depending on the response, say, capabilities or characteristics of the reserves. And then from event, we have the non-event or the normal conditions, changing system conditions. And we can categorize them as flexibility and the regulating reserve. And then, as we all know, for flexibility reserve, so the objective of this one is to correct the imbalance, the anticipated imbalance, say in terms of the ACE or the area control error. And this can be controlled manually as part of the optimal dispatch. And then on the other hand, for regulating reserve, so this corrects the real-time imbalances. And this has faster response time. And this is done automatically within the optimal dispatch. And then from the operating reserves, the question now is, how do we define dynamic reserve requirement? So as mentioned earlier by Debbie, so we have a rule of thumb requirement long time ago, which is called static reserve, which is a fix. And this is also dependent on, independent of system conditions. So unlike static reserve, dynamic reserve is the one that is, we define here is as the reserve requirement that change based on system conditions. And what you can see on this slide is just a quick comparison of how static reserve and dynamic reserve behaves in terms of balancing the system. And what you can see on the left side is on the static reserve, if the requirement is fixed, there's a tendency for the system to have some load balance violation, which is shown by the red area here. And then this is where the advantage of dynamic reserve comes in. On the right side, after doing setting the reserves requirements dynamically, the load balance violation disappears. And then from the definitions, so let's move on to the overviews of the existing dynamic reserve requirements. Let's start with the short-term RAM products, particularly the ones in MISO, CAISO, and then SPP. So for MISO RAM products, so these are some of the key features of the MISO's RAM capability product. So this is composed of up and down capacities, which is called up RAM capability and down RAM capability. And then this is procured in day ahead and real-time markets. The main objective of this product is to manage net load variations. So meaning these are the changes in the net load from one horizon to another horizon. And then also from variations, it also addresses uncertainties. So this is more on, see the forecast error, real time versus what is forecasted. And then MISO's RAM product is implemented system-wide. And the requirements are based on two components. They have net load uncertainty and then net load change. And then as I mentioned a while ago, so uncertainty here is calculated based on errors coming from load forecast, wind generation, as well as the dispatchable resources that are not following the set points. And then for the net load changes, or the changes from one horizon to another, so this is also related to the changes in load forecast, wind generation, and also net scheduled interchange, or NSIE, in MISO. Oops, sorry. And then from MISO, let's move on to CAISO. So there's a pretty similarity to MISO in CAISO's flexible ramping product in terms of they also provide the up and down capacities. This time they called it FRU, or flexible ramping up, and also FRD, or flexible ramping down. And then this is also procured in real time, which includes a real-time unit commitment, which includes a 15-minute market, FMM, and also the real-time dispatch market, which is a 5-minute market. And then again, the objective of this product is to address uncertainty that may happen in real time, and also to balance the operational challenges in the system, as well as to ensure that there is sufficient ramp capability in real time to avoid extreme prices, market extreme prices. In terms of the requirements, so the requirement is determined based on 2.5 and 97.5 percentiles of histograms of the historical net load errors. So we can see here, they use here a rolling data set of the last 40 days. And then lastly, let's go to the SPP ramp capability product. So for SPP, for this one, for more detailed, our presenter Kathryn will provide more details for SPP. This is just an overview. So what we can see here is SPP's ramp capability product also has the up and down capacities. And then they are procured in day ahead and real-time market, or real-time balancing market. Similar to CAISO and MISO, the objective is to address the uncertainties with increased renewables. And at the same time, to avoid the impact of price spikes due to ramp deficiencies. And then the requirements are calculated based on the forecasted net load changes and historical net load forecast error over a rolling 20-minute period. And one thing to highlight also is this product, this is the newest product compared to MISO and CAISO. This is just implemented this year. And then to summarize, so this is a high-level comparison of the 3 short-term RAM products. We can see that they have similarity in terms of they provide both up and down capacities. And then in terms of their time requirement, it ranges from 5 minutes to 20 minutes. And then the requirement method is based on expected variability as well as the uncertainty. The quantity requirement depends on the system. So yeah, see in MISO, it's up to around 2,000 megawatts. And then in CAISO, it's up to about 350 megawatts for upward ramp capability. And then in terms of the included market, they are included from day ahead to real-time markets. So from short-term, long-term products, let's move on to the long-term ramp products. So this time we'll talk about EirGrid's ramping margin in Ireland, and also MISO's short-term reserve product. For EirGrid's ramping margin, what we can see here is are the 3 categories of their ramping margins from ramping margin 1, 3, and 8. And then how do they define this? So they define this in terms of the minimum ramp up and output durations. So what does it mean? So for example, ramping margin 1, So the requirement here is this reserve or ramping margin requirement should be delivered within 1 hour, and then this should be maintained for 2 hours. And then similar to the other ramping margins here. And then the objective of this ramping margin in Ireland is to address forecast errors related to renewables, particularly over forecast errors. And then this requirement is included in their LTS or long-term schedule. So this is in Ireland, LTS is run every 4 hours, and this produces up to 30 hours of unit commitment schedules. The question here is how does it is it formulated in EirGrid? So this is how the ramping margin is formulated in EirGrid. So RMR here, so this is the ramping margin requirement. And as I mentioned a while ago, so the requirement is a function of LFE, which is the load forecast error, and also some of the uncertainties related to, so this variable is the uncertainty related to variable generation. And they also include the uncertainty related to tie line flows. And then from EirGrid's ramping margin, let's go to MISO's short-term reserve. So this is a new product implemented in 2021. And short-term reserve or STR, this is a 30-minute rampable generation capacity. This is provided by online or offline resources. This is co-optimized with energy and reserve services products. And this separately addresses market-wide, sub-regional, and local short-term reserve needs. And this aligns with the recommendation of the IMM or the Independent Market Monitor to implement a 30-minute product to incorporate VLR or voltage local reliability and RTD or regional dispatch transfer commitments into the market. And in terms of the requirements, both local and sub-regional, so this is determined by using reserve procurement enhancement or RPE constraints. So this is based on a calculation that is done dynamically. And again, this is based on the loss of generation elements and associated change in flow and the flow limits. And then to summarize, so this is how it looks like. So in terms of the time requirement for EirGrid and MISO, so it ranges from 30 minutes to 8 hours. And then the requirement method is based on expected variability and uncertainty in EirGrid. For MISO, so this is dynamically calculated through loss of generation and flow constraints. And what you can see on the two right columns here are also the long-term products that are not yet effective. You can see here CAISO's imbalance reserve and SPP's uncertainty product. And now let's move on to dynamic contingency reserves. So a while ago, we discussed about short-term RAM products and then long-term RAM products. Now this is the dynamic contingency reserves. And what you can see on the screen right now are some of the definitions of the requirements in the 5 selected ISO, RTO in North America. And what you can see here is the dynamic contingency reserve is they are always most of the time they are benchmarked with the largest first contingency loss in the system. And for example, for ISO NE, so the 10-minute reserve must be greater than or equal to the largest first contingency loss. And they can add or they may add a non-performance factor to increase the requirement. And this is based on the historical performance. And then for SPP, they apply an hourly scaling factor. In ERCOT, this is a bit different. So the requirement is a function of the anticipated system inertia, primary frequency response, diurnal load and wind patterns, and average temperature. And then for CAISO and AESO, so the minimum requirement is equal to the greater of the single largest contingency, and other benchmarks or requirements. For example, in CAISO, yeah, you can see items 2, 3, and 4. So in item 2 here, it says this is the sum of the 3% of CAISO's hourly integrated load plus 3% of CAISO hourly integrated generation. Yeah, something like that. And then I'll move on to the methods to determine the dynamic reserve requirements. So there are plenty of ways, and for this presentation, I'll show you some of the approaches that is also conducted here at EPRI. So there are two approaches that I will further show later. The first one is using probabilistic approach, wherein this can be categorized as recursive, anticipative, and hybrid. Under recursive, yes, Debbie?
Joanne, you have got 2 minutes left.
Oh, thank you. I will wrap up. Thank you so much. So under recursive, this is basically based on historical information. The advantage of this one is this tries to capture what happened in the past. The disadvantage is it cannot capture the rare events that can happen in the future, and that doesn't happen in the past. And then anticipative, so this is based on the shape and properties of probabilistic forecast. And then hybrid, this is combination of recursive and anticipative. And then for using iterative approach, this covers more on the iteration, which undergoes a learning process, wherein it trains the reserve activation factor, which I will show later. This is just a simple illustration of CAISO's case study done here at EPRI. I will not discuss this one in detail at the moment, but I'm happy to discuss more on this one later. But what you can see here is the top one here is the resulting reserves in the system using the 3 different approaches, recursive, anticipative, and hybrid. And then the chart at the bottom is more on the level of risk. And the highlight here is hybrid approach. It outperforms other approaches because it captures the benefits of both adding the historical and also the forecast. And then this is another case study. This is more focused on the iterative approach. On the left side, this is just the current practice in contingency analysis. The right side is the one that's formulated by my colleagues at EPRI, wherein the reserve activation factor is being learned over several iterations. And then the advantage of this one is you can see that the reserve requirements changes as the activation factor is being trained in the simulation. And this is just some example illustrations on how the hourly reserve is simulated over the learning process in the over the training in the process. And then the right side, this is a simple illustration of the results showing the graphical or the spatial allocation of the reserve in the system. And then as a summary, so we defined what is operating reserve. We defined what is dynamic reserve requirement. There are 3 groups that can represent the existing dynamic reserve products to date: short-term RAM products, long-term RAM products, and dynamic contingency reserves. And then we also provided some of the examples. And then there are also 2 approaches that can be used to determine the dynamic reserve requirement. One is a probabilistic approach, and then the second is iterative approach. And in the previous slides, we also showed you some of the demonstration on how these approaches can be used to determine the dynamic reserve requirements. And I hope and these are some of the key references that hopefully you'll be able to utilize in the future. And thanks for listening, and I'm happy to to answer your questions if you have questions. Thank you.
Thank you so much, Joanne. That was a wonderful overview of dynamic reserves, the status of what's going on in different parts of the world, and how people are thinking about calculating the reserve requirements. Next, we're going to have 3 speakers talking about specifically going into more depth in different regions, California, SPP, and New York. And I'd like to invite up to the podium Arne Olsen to talk about some California work that he's doing. Arne leads E3's bulk energy infrastructure practice, and he has over 25 years of experience in energy analysis, investigating deep decarbonization and high renewable scenarios for utilities across the country. Arne.
Hey, yeah, thank you, Debbie. Great to be here today. I think the last presentation was a great overview, and as Debbie said, we're going to go into a little bit more depth in some of those areas. So just to set us up, I think everyone in this room already knows the stuff that's on the first 2 slides here, but decarbonization will lead to massive increases in wind and solar generation, and it's really now everywhere. They're the lowest cost sources of clean energy everywhere in the country, even in New England. We expect to see much larger electric loads as we electrify end uses that currently use fossil fuels. That's going to require even more clean energy. And as we increase our reliance on weather-dependent resources to where they become large shares of our supply at any given point in time, it's pretty obvious that we're going to have to get a lot smarter and a lot more nimble in the way that we operate our power systems. Grid operators have always had this challenge of balancing variability, and they typically have done that through the definition and procurement of ancillary services or grid services, mostly based on load in the past, but also based on the potential for large events like large generators or transmission lines going out of service suddenly. The need for grid services will increase. You may be surprised to learn that wind and solar are subject to variability and forecast error. The need will become more dynamic as grid conditions change. And just to give you a little example of that, the chart on the right shows increases in ramping requirements for the CAISO system between 2019 and 2030 on the right. And you can see very large increases, multiples over that 10-year period. So these are the changes that the CAISO is gearing up to be prepared for. So I'm going to spend the rest of the time talking about a specific E3 project for which we received a grant from ARPA-E, and we're very thankful and grateful to them, and with which CAISO was our partner to, in effect, build a machine learning model to do dynamic operating reserve calculations. So it started with our gathering data from the CAISO for 2016 through 2018 on hourly and 15 and 5-minute load, wind, and solar forecasts, plus load, wind, and solar actual instances. Use that to train a machine learning model. That's on the top left there, using, and I'm really disappointed with myself that I didn't get this term into my slide deck, using a multi-layer perceptron, which is a form of artificial neural network. And that might mean something to some of you. I have a dim notion of what that specifically means. But in effect, we're throwing as much data as we can at this problem, at this very complex problem, and trying through the power of machine learning to glean from that data what the patterns are, how these things vary, how they vary together, what the relationships among the variability are. What comes out of that are reserve requirements, which I'll get into. So then we tested our dynamic reserve requirements on the CAISO 2019 system to determine whether there really are any production cost savings or emission savings. And then we compared that to the current CAISO method just to get a sense of, is this really a promising direction or not? So Joanna already talked about the FRP product in the CAISO system. That's the product that we chose for our demonstration. It's not the only product, or maybe even the highest value product that machine learning techniques could be used for, but it's one that's relatively simple. There is a lot of repeated data over that 2016 through 2019 period. So we had a lot of data to work with, and it's really a proof of concept. We think that the techniques could be applied much more widely. But we zeroed in on this FRP product. It's a 15-minute reserve product that's implemented in the CAISO's energy imbalance market. It's designed to ensure that each participating balancing authority area has enough flexibility so that the EIM can clear on a 5-minute basis. So in effect, it's a 15-minute reserve product that sets aside capacity so that the 5-minute market can clear and not see any unserved energy or not contribute to ACE. So our reserve tool takes in data from forecasts of load, wind, and solar at previous time periods. It was trained, as I said, over a 3-year period. But when we actually go into the operating day, we have real-time information available to us, and we bring that into the model and use it to calculate FRP requirements upward and downward based on the most recent information available about the grid conditions at that time. So this chart kind of illustrates that. If I can figure out how to, there we go. So T0 here in the middle is the time when the window closes on your predictions. Prior to that, and so at that time, what information do we have available? So looking backwards, we have 2 instances of 15-minute load, wind, and solar forecasts for a 15-minute time step. And we have 6 instances of 5-minute load, wind, and solar forecasts. So the most up-to-date information about, is it cloudy or not? Is it cloudy everywhere? Is it only cloudy in some places? What is the load looking like? Whatever the most recent information is about all those things, we bring those into the model. At T0, then we say, given all that information, what's our expectation of the potential envelope of net load in the upward and downward direction over the next future interval? That next future interval isn't the next 15 minutes. You have to wait for 15 minutes. So it's in effect at T0, you're setting up the system for T0 plus 15 minutes to T0 plus 30 minutes. And then this interval in the middle, you're using the previous iteration, right? So at T0, what's my forecast? And I've got 3 5-minute intervals that I'm worried about. So there's the first 5-minute interval, the second 5-minute interval, and the third 5-minute interval. So what's my expectation of net load variability for that, each of those 5-minute intervals, 15 minutes from now? Hope that's clear. If there's anybody has any quick clarifying questions, I could take it now, but hopefully that's clear. Okay, so just getting into some of the results of this process. So here's some example days of machine learning time series data on load, wind, and solar errors, and aggregating up to a net load forecast error. So on this specific day, we have our demand forecast for 24 hours times with 15-minute and 5-minute periods within each hour, and same with solar and same with wind. You can see here that there's the red line is the actual forecast error for that day. Sometimes you were right on, sometimes you were too high, sometimes you were too low. The shaded bands are the uncertainties that were calculated by the machine learning model. So that darkest band is the 25th to the 75th percentiles. So 25th percentile below, 70th percentile above. So that darkest band is capturing 50% of the forecast errors. The next band is the 5th to the 95th percentile. So it's capturing 90% of the net load forecast errors. And then the lightest band is 2.5 to 97.5. So it's capturing 95% of the forecast errors. We have these, we start with load, wind, and solar forecast errors independently. But what we're most interested in for operating reserves is understanding how those interact with each other and what the net load forecast error is. We don't care what solar is by itself, wind is by itself. What we really care about is what's the net load signal that all the generators have to respond to make sure that we can keep our system reliable. And these things combine in very complex ways. They're certainly not just additive, because sometimes load goes up and solar goes down, and wind goes up when solar goes down, and vice versa. If they were all completely independent, you could use the sum of squares method to add up all the variability. but in fact, they're not. In fact, the statistical relationships are quite complex among these different stochastic variables. This was what makes machine learning kind of an ideal tool to understand. You can just throw a lot of data at it, and the machine learning tool will derive from that data what those statistical relationships look like. And then at the top, what we end up with is our net load forecast error, again, with all these different percentiles. And we can pick which percentile we're interested in, how certain we want to be that we're covering all those errors with our available capacity. And for the rest of the study, we've picked that most stringent, the 97.5th percentile as our rule. And that's following along what the CAISO has done with its histogram method. So you can see that these variables are dynamic based on grid conditions. They change throughout the day. They change with load. They change with wind generation. They change with solar generation. And they're more dynamic when the grid conditions are more dynamic. So on the bottom right is a more extreme day where we had a very large forecast error. We're interested not just in average conditions, but under extreme conditions. How good is our model at preparing the system for the potential for large forecast errors? You can see this red line here was a real forecast error that happened on this day, right around 8:30 a.m. And if you look closely at this, and you probably can't see it from the back of the room, but our model didn't quite capture the highest peak. We were a little bit slow, but was pretty good at anticipating that this event might occur. And similarly, there was a big error in the downward direction at the end of that day. And our dynamic reserves did a pretty good job of anticipating that and preparing the system to be ready to meet those. So comparing this now to what the CAISO is currently using, and Joanne talked about the histogram method that they're currently using. This is just zeroing in on a specific day, June 7th of 2019. You can see there was a lot of noise on this day, a big net load under forecast in the morning, a bit of an over forecast late morning, a bit of an under forecast again around sundown, and a bit of an over forecast again at night. So lots and lots of variability on this day. You can see that during some times our machine learning tool really anticipates that there might be a large error right around sunrise. And so it's preparing the system to have a lot of flexibility, a lot of headroom and footroom right around that time. But during the middle of the day, based on the conditions it sees, it says you can be a lot skinnier now, based on the solar forecast and the load forecast. It doesn't need as much flexibility during the middle of the day. So what we see then compared to what the CAISO's method does is that the look back histogram method, there are times when it falls short. There are times when it produces a lower amount of reserves than our tool would produce, but also a lower amount of reserves than the actual forecast errors. So it's short in some hours, but it's really long in a lot of other hours. It's quite a conservative really view of what the flexibility that the system needs. So there's a lot of extra expense in these hours here where it's carrying all this headroom and room, all these extra reserves that it might not need. And just to give you just to clarify, their method uses this 20 to 40 day backward looking window. It's really based on time slices. It's not, again, based on dynamic load and solar forecasts. There's some interesting dynamics that you see when you start to examine this variability in the forecast errors closely. One of them is that the amount of operating reserves needed is a function of the amount of renewable generation that you have. More specifically, the forecasted renewable generation. Now that's intuitive, but the relationships are interesting. What we actually find is that when it's really, really sunny, so when solar is producing near its maximum, the amount of reserves that you need are lower. And when it's producing near its minimum, the amount of reserves that you need are lower. So the reserves are highest when it's in the middle, when it's a partly cloudy day, clouds are coming in, they're covering the panels, they're going off the panels, they're moving back and forth. That's when you need the most flexibility. And it does make sense if you think about it. So if your solar is producing at its maximum amount, it's not going to go really much higher. So intuitively, you don't need to carry a lot of downward reserves in case that solar goes higher, right? And similarly, when it's near its minimum production, it's not going to go any lower. So we don't need to carry a lot of upward reserves in case the solar goes lower. So that's again, when I say that these relationships are complex, they're dynamic, the actual statistical distribution, if you were to calculate it, would change based on grid conditions, which again is why it's impossible to solve just using convolution mathematical techniques. But we can solve it by throwing lots of data at it. And by contrast, the histogram method completely misses these dynamics. So this red line here is what the histogram method would tell you to reserve in the upward direction. It's almost entirely insensitive to the amount of solar that's on the system, and similarly in the downward direction. So it has too much reserves during very sunny time periods, and potentially not enough reserves during the middle, when the solar is more variable and the net load is more variable. So just some statistics as to how our machine learning tool compared to the histogram method over many, many hours over the entire 2019 period that we simulated. This coverage metric tells you how close we got to our 97.5 percentile target. We designed both the histogram parameters and the reserve tool parameters to cover 97.5% of the upward deviations. The CAISO method, even though it was designed to get to 97.5, only gets to 94.4%, and our reserve tool got to 97.3. So we didn't quite hit our target of 97.5, but came very close. So we have better coverage than the CAISO model. We reduced the FRP needs on average by about 20%. So we just take the average over the entire year. With the histogram method, it was 776 megawatts, and we reduced that to 614 megawatts. And there's some cost savings and some GHG savings associated with that. When we did miss, so when there were times when the actual forecast error exceeded our 97.5th percentile marker, our misses were smaller. So the average miss with the histogram method was 234 megawatts, which is 152 megawatts with our reserve machine learning tool. And then when we missed really, really badly, and I'll talk about this on the next slide, the reserve tool missed much less badly than the CAISO method. So the CAISO's worst error was a shortfall of 3,350 megawatts, which that's kind of a big number on a 50,000 megawatt system. And the reserve tool's biggest miss was 1,700 megawatts. So our conclusion from this is a pretty promising methodology. Zeroing in on those extreme events, because we think there are both economic and environmental greenhouse gas benefits to these techniques, but we think there also are reliability, or we were interested were there also reliability benefits to this. So we wanted to zero in on what the worst misses were looked like. So this is a plot on the right of the predicted net load forecast error on the x-axis and the observed net load forecast error on the y-axis. And the red dots here are the results of the histogram method, how much reserves the histogram method was telling you to hold. The blue dots were how much reserves the machine learning tool were telling you to hold. So ideally, all of these plots would be right on that 45-degree line. That would tell you you were getting everything exactly right. Of course, we didn't expect that. But the patterns are really interesting. The red dots here indicate that the histogram was predicting less than 1,000 megawatts of upward forecast error in times when there actually were over 3,000 megawatts. So these were really, really big misses. And for those same events, our machine learning tool was way over here in this kind of 2,000 megawatt range. So it was much better at predicting, at preparing the system for these very large forecast errors than the histogram method. Now it's sometimes by as much as 2,000 megawatts. There's some hours when reserve was saying to hold 2,000 megawatts more than the histogram method was, and we still were undershooting what the actual forecast error was. And it's still hard to quantify the reliability benefits of just having that much more reserve when there's a big event. but intuitively, it seems like it should be pretty important. So we tested the quantitative and cost benefits of this using a PLEXOS model of the CAISO system for 2019. We did one simulation using the histogram method to determine the flexible ramping reserves, and one simulation using the machine learning tools, flexible ramping reserves. And we found the delta was about $19 million per year of production cost savings. So that's real savings. You know, it's not 100 million, but it's also not, 1 million. Feels like it's worth going after. Greenhouse gas savings were about 130,000 tons per year just from more efficient operations, 0.2% reduction in the footprint-wide GHG emissions. So that was pretty good for just this minor tweak to the way that they do operations. Curtailment was reduced by 19%. This case doesn't have flexible ramping from solar. So if we allow solar also to provide flexible ramping reserves, the savings are about doubled. So that's another interesting finding, and it's complicated to do that. So we didn't put that on our base case, but just to know that significantly increases the potential. We did a 2030 case as well and learned that if we actually build the 12,000 megawatts of battery storage that California is planning to build over the next 10 years, that a lot of these savings go away. You can make this problem almost entirely go away if we throw billions of dollars of capital at it, is what we learned. May make sense to do that for all kinds of other reasons. But we still think there's value in making sure that we're building the right amount of storage and not just throwing lots of money at the problem. Now, to be fair to the CAISO, they are already in the process of updating their FRP requirement calculations with a much more sophisticated method, capturing some of the benefits that we show here. We did have a little bit of a chance to compare ours to the new method, and our machine learning tool was still better than the new method, but not by as much. So then lastly, we concluded our ARPA-E grant. There's a paper coming out next month in the Journal of Renewable and Sustainable Energy. So we can look for that. Our next steps for the tool, we definitely are using it for lots of planning projects. A lot of utilities are using it themselves to help give them a vector of reserve requirements that they can use for planning and procurement. We're discussing application of reserve in a day-ahead scheduling and operations with a number of utilities. So the idea there would be, and we have one utility that's doing this, using the tool to calculate what really is a set aside on their flexible capacity at the day ahead time period, which informs their commitment and informs their wholesale trading, so they can make sure they're coming into the operating hour with enough headroom and enough footroom. And we think there are lots of other potential applications of these techniques to operational problems. So just for example, informing battery state of charge requirements. If you really want your batteries to be there for reliability, you don't want them necessarily to chase down every last dollar of arbitrage opportunities. You might want to have them set aside some capacity. You can use machine learning to help you figure out how much capacity, how much state of charge you want them to set aside. You can use it to determine how much solar or wind you can rely on for upward reserves, which is itself is a stochastic problem that's dynamic. It's a very similar problem. And we think you could also incorporate thermal power plant outage risks into your commitment decisions as well. Lots of other applications. So yeah, with that, thank you.
So much. Thank you so much, Arne. That was a fantastic explanation of a new way to look at reserve requirements, and certainly shows how CAISO has come a long way from that old swinging door flying brick method they used to do decades ago. Anyway, we're going to now switch gears to New York, and we have Rana Mukerji, who's been at the New York ISO since 2006, where he's responsible for market design, product and project management, strategic and business planning, research and development, and market training teams. And before he was a senior vice president at New York ISO, he was at ABB and also at GE in energy consulting. Rana, I'm going to turn the floor over to you.
Great, Debbie, thank you. Can you hear me and can you see my screen?
Yes, we can hear you and we can see your screen. Perfect.
Excellent. So yeah, I wanted to thank Charlie Smith for inviting me to your very important meeting. And I'm sorry I couldn't be in sunny Denver in person, but very happy to participate virtually. So I'm going to give you a little kind of an in-depth view of what New York is doing in terms of dynamic reserves. And I believe, as you mentioned, this is a very important topic in terms of moving the integration of renewables into our markets and into the system as we move towards decarbonization of the grid and of the economy as a whole. So I think this is a very important step, and I'm happy that you have put a focus on it. So in New York, it used to be that California was always in the bleeding edge, and New York was probably half a step behind, but our goals right now are almost as ambitious as California, in some respects even more so. So what the New York State's goals are to get to 70% of energy to come from renewable sources by 2030 and 100% carbon-free by 2040. And that would, these are codified into a state law called the Climate Leadership and Consumer Protection Act. And it means that, and some of the targets are 6,000 megawatts of solar by 2025, going to 10,000 in 2030, 3,000 megawatts of storage, 9,000 megawatts of offshore wind, and all of that in a system which has a historic peak load of about 33 gigawatts. So this, this is the trajectory we are in, and one of the ways that we looked at it, we did a lot of analysis on how do we get there, what kind of resource mix does it take to get to these goals. So we spent the last 2 years or so doing some in-depth studies on system expansion to find what it takes to get to these goals. So this is interesting. What we find is that today, with this peak load of about 33 gigawatts or 34 gigawatts, we have an installed base of just over 40 gigawatts. And when we get to the 2040 goal, the capacity goes more than 3 times, 140. The energy about doubles, and some of it is driven by electrification, because really this should be a cause of joy for anybody who works in this industry, because the key to decarbonizing the economy is to electrify everything and move everything to the electrical system, in all the energy requirements into electricity, which should be great news for all of us in the industry. And how we do that is to build a lot of renewable resources, wind, solar, and also build storage to back it up. So the whole question is, how do you back up the intermittent nature of the renewable assets? So one thing I would point out is that in our simulations, the light blue bar in the top, very top, if you see 2040, the light blue bar is the storage. And then contrast that with the orange bar in the bottom. We have today about 30 gigawatts, out of the 40 gigawatts of installed base, about 30 gigawatts of gas turbine combined cycle gas-fired units. You will see that if you look at the capacity up to 2040, the capacity remains kind of constant, and with a slight increase, even if you go to 2040. But if you look at the energy, you see the energy, these units are there, but they run less and less. And by 2040, they switch to renewable natural gas or hydrogen or some other carbon-free product. So you would need what we don't call these gas turbines, we call them dispatchable emission-free resources. So we don't believe that it could be a long-duration battery. We don't believe that the current, like the 4-hour, 6-hour lithium-ion battery gives you the long-term storage needs that is needed to balance the system. Now, if you look at our growth of intermittent assets, it's huge. It goes from if you see the capacity going from 40 gigawatts to 140 gigawatts, and all of it through mostly intermittent resources. There's a lot of intermittency we add into the system. And as I've mentioned that for many years now, that one of the key ways of actually integrating intermittent resources is through forecasting. And we spent, since 2008, we've spent a lot of time a lot of resources to perfecting our wind forecasting systems, solar forecasting systems. We recently did a very sophisticated system which allows us to even forecast the behind the meter solar. So forecasting is a key, and that we've been working on for many years. But the next thing really is to look at how much reserves we procure to back up the resources which are intermittent. And that's where dynamic reserves comes in, and that's why it's very key. And the other thing, which is very important, especially for markets, if markets are going to sustain the growth of renewable energy, is that there should be proper price formation. And in terms of price formation, what I point out is that price formation is to incent resources to act in a way that they reinforce reliability. So if we need ramp, you should have high prices so that resources which have ability to ramp have incentive to ramp. When you want to ramp down, you should have corresponding prices as well. So the price formation is very key, and price formation is driven by what you offer into the market, how much supply is there, and what the requirements are set. So requirements is where how much, and in terms of requirements, a lot of it is how much reserves you procure. So dynamic reserves is also very key to price formation, which is also very key to maintaining reliability. So that's one of the reasons I kind of started with what the resource mix is, and I'll talk a little bit about price formation. So price formation is important for all resources, conventional resources, renewable resources, batteries, everybody needs prices. But one of the things that is happening is that there's a fear that a lot of these resources are zero marginal costs and prices will collapse. And that is not so. What we foresee is that prices will certainly get much more volatile, and they will be driven by, a lot of times they might be zero or even negative because of the marginal cost resources and transmission congestion, which might even drive negative prices. But there could be periods of very high prices, especially when you get to when you're using resources such as hydrogen, which are very expensive, which are used to balance the intermittency. So you could get periods of high prices. Ultimately, a lot of pricing will be set by price responsive demand and by opportunity costs. Batteries have so much energy, and they're going to price it so that they get the most revenues out of the market. So prices are going to be volatile, and they're going to be high, and they could be very high sometimes, and they could be very low. So we have to prepare for volatility. But the main thing is market prices should incent the right behavior to reinforce reliability needs. And that's where ancillary services comes in. So, and it's no longer ancillary. Ancillary events are the main event right now because they do drive prices. How much reserves you procure preserves reliability as well as drive the prices, because they are co-optimized in our markets, at least, with the energy. So reserves and energy, ancillary services, reserve regulation and energy are co-optimized. So when you are hitting the reserve limits, you are going to also have higher energy prices. So ancillaries are no longer really ancillary. They are really the key event in terms of market pricing. The other thing is the markets like New York and the Eastern ISOs, New England and PJM, which have capacity markets, are also very important. The capacity markets provide fixed cost revenue needs to satisfy them, so-called missing money. And the reason, and a lot of resources, including renewable resources and batteries, depend on them. One of the key things that we are doing here now is in New York is that we are doing what is called capacity accreditation. Arne actually helped us a lot on that, in that front, and so does GE Consulting. Is basically on what's the resource worth in terms of capacity. We know what a gas turbine is worth, but what's the 2-hour resource of 2-hour storage worth compared to a gas turbine versus a 4-hour battery versus a 6-hour battery? And we've seen that for a battery to be approximately equal to a gas turbine, it takes 8 or more hours of storage. Similarly, what's the wind resource worth? What's onshore wind worth in certain location versus offshore? What's solar worth? In solar, it's worth about 40% in the summer, a lot less than that in the winter when the peak shifts into the evening hours. So capacity accreditation for us is very important. But when we talk about dynamic prices, it's more about the energy market. So we'll focus on that. So today, in today's market, we set reserves on a more of a static basis. And it was driven in the legacy because resources were conventional, they were predictable, they were not much fuel limitations. So we based the capacity, the reserve requirements based on the largest generator contingency and securing the key transmission interfaces based on the N-1 consideration, system planning consideration. In New York, again, New York is a constrained control area, so we have many reserve regions and they are overlapping. K is Long Island, J is New York City. Between K and J, we have 65% or so of the load or the demand in New York. We have G, H, I, J, K as Southeast New York. We have NYCA. The New York City zone, NY is zone J, Southeast New York is G through K, and zone F is the capital region where Albany is, and then we have the New York control area. So we have over interlocking reserve areas, and we have requirements and demand curves for setting reserve prices set there. And if say that Long Island has less than 6,000 megawatts, more like 5,000, 5,500 megawatts of demand, but there is going to be 9,000 megawatts of offshore wind off of Long Island, and they're going to sink into New York City and Long Island more like 2/3, 1/3 basis. So 1/3 in Long Island, 2/3 in New York, and it could be more than 9,000 in the future. So when you have a load of 6,000 and you got 3,000 megawatts of wind sinking into Long Island, how much additional reserves do you procure in Long Island? How much do you procure in New York City? So those are the kinds that do you keep them static? We believe that keeping them static would cost more. So we certainly have to adapt them to the system conditions. So that is one of the drivers for dynamic reserves. And just as I mentioned, the prices are set by the requirements and by what other markets refer to as ORDC, the operating reserve demand curves that we have. When we run short of everything, we can get prices close to 4,000. And that probably needs to go higher and potentially could go all the way up to value of lost load, such as what ERCOT has in the close to $10,000 per megawatt hour. So, which brings us to how do we set dynamic reserves? Arne gave a very sophisticated machine learning based approach. We look at probabilities as well. It's not as forward looking kind of as Arne mentioned, something that we would probably take a look at in the future. But this is based on extending what we do now and make the reserves procurement more dynamic and that we can implement relatively soon. I know that a lot of what Arne did is more kind of a study-based, more. I'm not sure when CAISO would be looking to implement these, but what we are describing here is what we want to implement in the next few years. So first thing we're going to look at is securing the reserve area for loss of generation. So today we procure it based on the largest source, and which would be based on the schedule for the largest generator. You can have a big, our 9 Mile 2, the biggest generator is 1,310 megawatts. Instead of procuring 1,310 megawatts, we do based on what the schedule is for 9 Mile 2, for example. We also want to look at when there are correlated loss of generators, when there is a single point of or there's a gas contingency, and we have to look at groupings of what generation groupings can we lose. We can also look at intermittent resource contingencies based on geographic areas and so on. So the first thing we have to do is to adjust the generation, how much we procure to secure for the loss of the largest generator, and also look at certain correlated events. The next thing we're going to look at is how much we have to set the requirement for the loss of transmission. So if there is a certain headroom, we also look at the post-contingency intermittent interface limits and also the current flow to find out how much we can depend on the transmission system to get into to provide reserves in a constrained area. And what we have to do is to look at them simultaneously. So we have to look at the largest generator contingency and the most restrictive, look at how much we can depend on the transmission area, and the more restrictive of the two actually sets the reserve requirement for the constrained area. So that's one part of our formulation that we are looking at. We are also looking at the probabilistic. We are not looking at machine learning, but what we are looking at is we have spent a lot of time looking at a forecast. So we schedule our generators based on a P50 on the 50% confidence level of what we expect the intermittent generation to produce. We would procure reserves based on the difference between, say, a P50 and, say, a P95. If we think a P50 forecast is 1,000 megawatts and the P95 forecast is lower, it's going to be lower than that, say it's 500. We have 50% confidence that the wind will be more than 1,000 megawatts. We are 95% confident it's going to be more than 500. So we might procure reserves based on the difference or a multiple of that difference. So and we would add that to the reserve requirement. And again, we would pick the one which is most restrictive between the largest generator, the transmission constraint, and the difference in between P50 and P90, 95, whatever we pick. So here's an example that we have two intermittent resources. The combined energy schedule is 1400 based on P50. The forecast for P95 is 1000. There's 500 megawatts of headroom. And we put a multiplier of 2, basically saying that say that this is a 30-minute reserves, we would procure twice the difference between the P50 and a P95. So the P50 forecast is 1400 megawatts. The P95 is 1000. So that there's an energy mismatch between the schedule and the P95 of 400. For 30-minute reserves, say that we pick a factor of 2, so we need to procure 800 megawatts of reserves, but we can depend on the transmission headroom of 500, so we would establish a reserve requirement of 300 megawatts in that constrained area. So. And again, this is what, say, 30-minute reserve. For spinning reserve, the factor could be 0.5. For 10-minute, the factor could be 1. So not only we do it based on different types of constraints, we'd also do it based on different flavors of the reserve, whether it's spin, 10-minute, or 30-minute. This is in that the probabilistic area here is we base it on the difference between a P50 and a higher confidence level. So this is basically what we want to incorporate in our market systems, which I know that Khosrow from formerly ABB is here. So we work with the Hitachi ABB team to formulate that in our market software and into production. And we've done some prototyping, and we want to move into the more of the implementation stage in the next few years. So some of the areas.
Rana, there's 2 more minutes.
Okay, so I'll give you very quickly what we are trying to do here, some of the use cases, which would help us to actually import more from Quebec. Quebec's imports from Quebec is limited by our largest generator, which is 9 Mile 2, which is 1310. It doesn't make sense to limit the imports from Quebec to 1310 based on our largest generator in New York. If it makes sense, we can go above 1310 from Quebec all the way up to what's available on the thermal limit of the transmission system, but we would have to procure more reserves. So if it makes sense economically, we could increase the reserves and import more hydropower. So that is one. We use certainly constrained areas like New York City. We will look at what reserves are available outside of New York City, but also based on what transmission headroom is available into New York City to adjust the reserve that we are carrying inside of New York City. We would also look at what we talked about in the P95, P50 intermittent forecast as the basis for setting reserves. We would also look at export constrained areas like Long Island, where we don't allow, for example, today Long Island to supply reserves into other areas because they're very, very limited transmission between Long Island and New York City or out of Long Island, but we could adjust that based on conditions, and if we were allowed to set reserves dynamically. And then we could also use this to set more areas, more granular areas, more load pockets where we could we now can be more nimble or dynamic about setting the requirements in these additional load pockets. But in the end of the day, I go back to the if you keep static reserves, I believe it just makes the system more inefficient and more costly, and economics terms less efficient. So essentially, if you're static, you're going to over procure reserves, which costs more money, and you need to do it smarter, and you need to understand the system conditions. You need to have an appropriate level of reserves to cover errors in your forecast, and which would actually make system more efficient, more cost effective, increase system performance, and enhance reliability. So that's kind of a preview of what we are doing in New York, and we'll be very happy to answer questions in the discussion session. Thanks.
Thank you so much, Rana, for that excellent presentation of a big overview of everything that's going on in the New York ISO with respect to decarbonization, and for how you're looking at dynamic reserves in the future. We're now going to switch gears to the Southwest Power Pool. So we have Kathryn Dial, who is a senior technical analyst at the Southwest Power Pool with 11 years of experience in operations. As a member of the SPP Uncertainty Response Team, Kathryn is focused on risk management at the balancing authority level in a region that has surpassed 90% instantaneous renewable penetration of load. So with that, Kathryn, I'll turn it over to you.
Hey, thank you. Can you hear me okay and see the main slide?
Yes, we can hear you and we can see your slides.
Okay. Great. Well, thank you so much, and thanks for the introduction. You know, you're absolutely right. I'm a senior technical analyst at SPP right now, but an electrical engineer by degree and schooling. So we'll dive right in here. And so SPP has really worked at length with our stakeholders to develop this new uncertainty reserve product, and it's currently filed with FERC and awaiting approval for implementation. And so that's what I want to talk to y'all about today. But a little bit of background on some of the considerations that we had to deal with when making this new uncertainty reserve product. So of course, you know, as you mentioned, getting over 90% instantaneous load being served with renewables here in SPP, that's huge for us. So we are seeing increasing penetration of variable energy resources. You know, I've seen it over the last decade just become huge for us, and it seems year over year we continue to grow. We set new records, and we're seeing annual energy, you know, an increasing share of that is being served by renewable resources. So it's not just those instantaneous peaks, but it's really just throughout the year that we're seeing this. And what we noticed is that even if resource forecast does not decline in accuracy, or, you know, maybe if we even make some marginal improvements in it, the impacts of even small percent deviations become more severe as that total installed capacity increases. So certainly something that we need to respond to. But additionally, another, you know, impact that we're seeing that goes right along with that is conventional generation retirements, of course. And so as those move out, we need to get creative and think of some new products to come in and help us. So this is a concern for today and for in the future. You know, we have infrastructure that's aging. It's not economically feasible for that to stay online. So that's going to push us more into reliance on variable energy or other alternatives such as flexible demand, which is just going to add complexity to the system and drives more needs for uncertainty type products. Additionally, and getting ahead of myself here. So additionally, what we found in 2018 that really spawned the uncertainty response team is that in the absence of an uncertainty reserve product in the market, what the market may do is it may economically commit all of your short lead, or at least most of your short lead generation across peak, and leave very little offline capacity to respond to intraday uncertainties. So, we realized that was something that we were getting into, and that could be a rather precarious situation because, of course, during those times, your exposure to risk is heightened if you're meeting your total obligation, but you don't have anything additional offline, no short-term reserves to manage forecast errors or resource plan changes. So that was certainly concerning for us and something that we wanted to respond to. And so that's where, again, the uncertainty response team came from, is those types of issues arising on the system. And one of the big answers that we arrived at for this was the uncertainty product. So getting into an overview of the product itself. So what we're looking at here is a product that's going to be applied to all of our forward-looking market studies, day-ahead market, reliability unit commitment studies, real-time balancing market. It's going to be cleared in all of those. So, as mentioned in an earlier presentation, we do have a ramp product that was recently put into production, and that's a really great product that we're leaning on now, but it's a 20-minute product, and it is cleared in both the up and down direction. But unlike that, the uncertainty reserve product is only going to be cleared in the upward direction. Additionally, unlike the ramp product, the uncertainty reserve product can be cleared on offline and online resources. So really keying on those offline resources there that are going to be eligible to clear this product as well. Additionally, this product has a 1-hour horizon, so that's going to allow for more uncertainty to be realized over the course of an hour than the 20 minutes that you see with the ramp product. So it'll be a larger requirement, so we expect, possibly you will be able to clear more resources, perhaps even more day ahead, slightly longer lead resources as well on that. So excited about that. And then as it looks like so many others seem to be arriving at this 97.5th percentile net load forecast error, that's where we landed as well for the uncertainty product. And again, that's net load errors over the 1-hour horizon. Now, this is not something that's going to be editable in real time, but we are allowing flexibility for the operator to adjust the final value should we decide we need to carry more reserves, say we were in conservative operations or something like that. It's certainly, we could increase our requirement during those time frames. But for now, we are sticking with that 97.5th. Seems like a good landing spot. And those errors are based on the same month and hour of the day from the previous year. But we'll move ahead here and kind of look at the concept diagram. And I think this gives, a good idea of what we're looking to protect against here, of the uncertainty that that we're talking about when we talk about this product. So again, only in the upward direction on this one, but what we're trying to protect against is that unforecasted upward movement in our net load, where net load for us is the system load minus your wind and solar generation, and then we add back in any net scheduled interchange over that hour. So, this is the type of behavior on the system that may at times require contingency reserves to respond to, but that is not the proper use of contingency reserves. So we absolutely needed a longer time frame reserve product to respond in these increases in the net load. And we want to be able to compensate resources appropriately for providing that service and that type of response and flexibility. So again, what you're just looking at here is over that hour. The black line there is your expected net load changes, and then the red line on top of it, that's that additional uncertainty that you can realize over an hour at that 97.5th percentile error. All right, well, I will go ahead here. And we can get a little bit here into calculating the product requirements. So how we decided to break this up is it has a planned component and an uncertainty component. So of course, the planned component there, that's your expected ramp, that's your forecasted ramp over the specified time horizon. And then the uncertainty components based on that historical net load error from that previous year, same month, same hour of the day. And then we combine those to get a 1 hour flexibility requirement. And then to get our uncertainty reserve requirement, what we do is we take that 1 hour flexibility requirement and then we subtract out any regulation up, contingency reserves that we're clearing, and then our ramp up that we're clearing as well. So we're going to back those out. And then what we have left is our uncertainty reserve requirement. So again, no downward product for uncertainty reserve. And we define all of these in terms of net load. All right. And then I'll go to the final slide here and just spend a little time giving some examples of the calculation itself. So turn my pen on here and we'll look at these. All right. So really looking maybe at 1400 here. So your forecasted net load change, you're going from, for 1400, we're going to go from 29,000 to 30,000 in our net load. So our 1 hour planned ramp is 1,000. And then we go back in and determine our 97.5th percentile uncertainty error is 755 megawatts. So our total 1 hour requirement is 1755. But then we go in and look and, well, what we're clearing for regulation up, contingency reserve, and ramp capability is 2,000 megawatts. So that's sufficient there. We don't need an uncertainty reserve on top of that because we're already meeting that 1 hour flexibility requirement with other products. Okay, so you can see it's 0. But looking ahead at 1500 into 1600, we know that we've got a 1 hour planned ramp of 2,500 megawatts for this particular hour. That uncertainty error that we want to protect against is 492. So our total requirement there would be 2992. And then again, our total reserves that we're clearing outside of the uncertainty product is about 2,000 megawatts. So there is a deficiency there of 992 megawatts, which we would use the uncertainty reserve product to fill that in. And so, we're certainly excited about that and about having this product to fill in for us, the gaps that we're seeing today. And, I will add that a little bit on here about the, our hope here is to incent the right types of resources and flexibility that we need on our system to, to provide these services that we're running into these needs, and to ensure that those offline resources aren't getting held back but are able to clear this and get compensated for that flexibility as well. So that is actually my last slide, and I know we went through that a little quickly, but well, I'll give you a little time back and open it up for questions.